So in the previous video, what we did is we tried to predict an output using a simple neural network architecture, and we've done that through the sigmoid activation function. We also uh, learned how to combine these different inputs and use this value that we get from the combination function into the sigmoid activation function, and this gave us a value. So this is what we did quickly, briefly, what this is what we did in the previous video. But then what we want to do now is to update those weights, because you remember that we have got a predicted value of y, uh, the predicted value of your predicted output rather. Like in the previous case, we've got a predicted output of 0.874653. And as I told you, maybe the real output, the output in your data set is 0.8, but what you're predicting is 0.87. So you want to update that weight, those weights rather, to give you another predicted output which is closer to 0.8. That is the idea behind, and this is what we are going to do today in this video. We are going to update these different weights, and we are going to update that through a method that we call the backpropagation rule. And the backpropagation rule, to be able to understand what it is, we need to understand what the gradient descent method is. And when we have understood what the gradient descent method is about, then we will be able to move on to the backpropagation rule. But before we get into the gradient descent method now, it's important that you just remember some notations here. We've got some notation like the first thing is that you had the sigma x, which were these fx that we had in our neural network when in the first video. These are our fx, our sigma x, and then what we have also are our net j. The net j value is the sum of wij xij. And this is what we did here, the net j, net a, this is net b, this is net z, and this is what we did in the previous video. So please refer to the previous video to understand how we computed this value, these values. So these are the values that are going to be used as input for sigma net A. The 1.2843 is the one that we use in to obtain sigma net A. But I'm not going to get into this again. We've already done that. So we'll just move on. And here, what we want to do now is to update those weights as I told you. But to be able to update those weights, let's take another notation. One of the notation that is net j. The other thing that you need to know is sigma x, which is here. One of it is net j. The other notation that we are going to use here is ED. ED represents the sum of squared errors. And the sum of squared errors, as you already know, when we talk about the sum of squared errors, you have your y minus y cap, right? You have your y minus y cap that you have generally. So you have your y minus y cap to the squared, and you have your sum of squared errors. So you have your errors which are squared and you're taking the sum. So it's the same idea here. Your y is our target output. Your oj represent the ok or oj represent our predicted output. It's like the tk represent the 0.8 in the example that I just mentioned, and the 0.87 something that we got here was a predicted output from the neural network, from the first pass of a neural network. So the OJ value is this, and the TK value is the TJ value is this targeted output. So the targeted output, in our case, we have only one output node, so we have O1 and T1. There is no more than O1, there is no more than T1. But if you have more than one output, then the sum is important to take into account, because then you are not going to just take 0.8 minus 0.87 to the square, but you would have to consider it for each and every node. This is why you have k in the summation. The k represent the different output nodes. If you have two output nodes, you will take t1 minus o1 to the squared plus t2 minus o2 to the squared. So in other words, this 0.8, this 0.8 that you have here, and the 0.87 is for one particular node. Then you have the same thing for another node. You will need to repeat this process and add them. But something else that you will note here is that there is division by 2. This division by 2 is not something that you are used to generally. You will just stick to this when we talk about sum of squared errors. This is what you do. The sum of squared errors is just that. But you will see that there is a division by 2. Why is this division by 2? It's just for mathematical purposes, and you will mathematical convenience rather, and we'll get into that when we talk about the backpropagation rule. So just bear in mind that when we talk about the sum of squared errors, it's just not the sum of squared errors in its traditional form that we are used to. The sum of squared errors is a sum of squared errors that is divided by 2 in our case, all right? And just bear that in mind. So, and we are defining it as ET. Having said so, the next step is to understand what the gradient descent method is. Now, the gradient descent method is a method that will update our weights in such a way that our weights are going to be updated by adjusting them. We are going to adjust these different weights in a certain direction. We are going to adjust these different weights in a certain direction where we will decrease the sum of squared errors. Now, why do we want to apply the gradient descent method? So I'm getting, first of all, you need to understand something, is that if you take the example of y is equal to beta naught plus beta 1 x1 plus epsilon, you assume linearity here. And when you assume linearity, you understand that the sum of squared errors will be something like that. You have a sum of squared errors, you have a beta 1 here, and the sum of squared errors will generally take a definite kind of shape, and you will have your beta cap, which will be obtained. And the beta cap is generally obtained through a closed form solution. A closed form solution means you have a certain formula, sum of squares of xy over the sum of squares of x. This is something that you've learned in other modules, where you have a closed form solution for your beta cap. But unfortunately, things are not like that in the context of neural network, because those weights cannot be defined like we are doing here. You don't have a formula that you can apply to obtain W nodes. You don't have a formula to obtain W1. These weights have been obtained randomly, and they have to be adjusted. And the way that they have to be adjusted, we need to do it in a different way. We can't just use a formula that will minimize the sum of squared errors like this case. We don't have such type of thing. So what do we do then? We need to find a way of doing it. And this is where we are going to apply the gradient descent method. The gradient descent method uses the same idea as you would have used for obtaining the beta cap 1, all right, by differentiating the sum of squared errors with respect to the weights. But in a linear regression, you will differentiate with respect to the parameters, but here you differentiate with respect to the weights. And the gradient descent method is going to be something like that. Let's suppose you have a certain weight, like in our case you have 0.8. Let's take an example here. You have a weight of 0.61. Right? Let's suppose you want to update that weight, only that weight. If you want to update that weight, what do we want to do? Let's suppose you have a weight 0.61 here, and the W1R is our 0.61, let's suppose. What you want to do is that you want to update that weight. You will see that the sum of squared errors, which is our ED here, the optimal solution is less than 0.61. It's going to be on the left here. But the current weight that we have is 0.61. So what do we want to do? We want to have an updated weight, a new weight, which is going to be obtained by taking the 0.61 that we have, plus a certain change in the weight, plus a certain change in the weight. So this is what we want to do to be able to obtain this new value. Now, the only problem that we have here is that the addition of that change is what is of interest to us. If we are adding a positive value, what's going to happen? We are going to move to the right, which means that we will not reach that optimal solution. However, if we are adding a negative value, then obviously we are going to move to the left. Now, what is this value that we are going to add to move to the left or move to the right? The principle is very simple. What we do is that we are going to obtain the change in the weight is going to be obtained by taking the change in the weight. Let's write it down as Wij. The change in the weight would be obtained by taking the derivative of the error by the sum of squared error by the current weight, which is defined as Wij. So the change in the current weight, which we are defining as Wij, is going to be basically the change, so the rate of change here, so d del Ed by del Wij. This is what we define as a change in the weight. But there is a problem if we use this definition as it is. Because when we use this definition as it is, just bear in mind, if you are talking about W1R, which is on the right of the optimal solution, let's suppose 0.61, you differentiate that function. Obviously, when you're differentiating that function, you're going to get a positive gradient. Whichever value this would be, it's going to be a positive gradient, which means that you are adding something with a positive value, which means that in the end, your 0.61 plus that derivative that you have here, let's suppose I could write it down here, del Ed by del Wij, when you are adding with that positive value, you are going to move to the right, you're not going to move to the left, because whatever value this could be is positive. So you are moving to the right, which is not good. So this is why you cannot take this value as it is, but you have to take the negative of it. By taking the negative of it, what's going to happen is that the value will move to the left. By taking the derivative of at this point, by taking the derivative at this point of a sum of squared error at this point, and you take a minus of a derivative, you will then move to the left. Now, if you think about, let's suppose you have something which is on the left of the optimal solution. If you added with del Ed as it is, without the minus, let's take this off. What would have happened? You have a negative gradient. If you are taking a value here, you are having a negative gradient. You are adding with a negative value. If you add with a negative value, in other words, you are moving to the left instead of moving to the right. So this is why you can't take the derivative, the positive value of a derivative. You have to always take a minus here. All right, you have to take a minus here. Just a minute review. You have to take a minus here. But now, try to understand something. If we define the change in the current weight as minus del Ed by del Wij, which makes sense. But the problem with that is that if you do this, you will see that the change, excuse me, you will see that by taking the derivative of its value, the problem that will happen is that you will move to the left, yes, but you will move to the left in such a way that you will move um, very far from the optimal solution. You will move very far from the optimal solution. And what would happen is that if you have a certain distance here between the optimal solution and this W1R, you will move by the same distance to the left. All right, around the same distance to the left. And what would happen is that you will get the updated weight here. You will get the updated weight here. So the current weight was here, the new weight will become here. But then when you come to this side, you will have to re-update this weight now because still far from the W star 1. So when you are going to update this weight using the same method, you will see that it will move to the right again at this particular point. So what is going to happen? Each and every time you will see that the value will keep on oscillating around the same two values, which is not a very good idea to have del ed by del wij. So this is why you need to add an additional term to it, which is eta. And this eta is going to represent what we call the learning rate. What is this learning rate? Eta controls the movement of your weight to the left. We have a negative which moves the weight to the left or move the weight to the right. But eta will control its movement. If you put eta equal to 1 as we did, it will keep on oscillating around two values each and every time. But if you decrease this value, normally eta will take any value between 0 and 1 generally. Eta will be a value that will lie between 0 and 1. So let's suppose if I decide to take, excuse me, suppose I decide to take a eta of 0.01. So what is going to happen then? If you take 0.01, it will make that change that was supposed to go on this side here go slowly. It will move slowly. It will move on the left, yes, but it won't move that much on the left, but it will move slowly to the left, slowly and slowly to the left. If you put it as 0.9, it will move very fast to the left. And when it moves very fast to the left, it will overshoot the optimal solution, which is not a good idea. So having a too small eta now, let's suppose you have 0.00001. You will move to the left, yes, but at a very, very slow pace. The change, the updated weight will move, but very slowly, slowly, slowly. Maybe it won't even converge to that. It will take an unacceptable amount of time to go and converge to the optimal solution, which you don't want. So this is why you need to find out an appropriate value of eta, um, which has to be through a trial and error basis again. You can't use an eta which is too big. You can't use an eta which is too small. Too big means um, you will overshoot the optimal solution and will probably not reach the optimal solution. Too small, it will take an unacceptable amount of time to be able to reach the optimal solution. So um, this is why you need to come up with with a sort of compromise here to determine this value of eta. So this is how we determine this change. And I'm going to so this is the change in the weight that we were talking about. What I will do now, I will try to show you how all this is, how all this operate on a small simulation in R. I will try to explain you that how the gradient descent method works through an oscillation in R, through a simulation, excuse me. I'm going to show you that there will be a set of codes that I'm going to write down, and you don't need to worry too much about the coding here because the coding is not important. It's just the result that you need to focus on. All right, just focus on the result. So I will create a set of values starting from, let's suppose, negative 10 to 10 in steps of 0.001. And if you want to have a look at these values, these are the values that we are talking about, steps of 0.01. So let me just rerun that. So I'm just going to rerun this so that you see what's going on. The codes. So here we go. I run the x, and then I'm going to create a y, which is x2 squared. So what is happening here? The x is like our weight w, and the y is representing our ed. Ed means the sum of squared errors. So we have the weights which are here and the errors which are defined as a x squared. All right. So in other words, what is happening is that we are facing a similar kind of situation here that you have, where you have y is sum of squared errors, which is our ed, and the x represent our weights. Okay. So what we want to do now, the first thing is that we want to plot that maybe, and I'm going to plot it for you by this code. I'm not going to explain to you the line of codes because it's not necessary. It's just for illustration purpose that I'm showing you that to explain to you how the gradient descent method work. Okay, but I'm not going to explain the code because it will be a waste of time here. So you can go through the code if you want afterward. Now, what we want to do is we want to update our weights. We want to update our weights, and to update our weights, what we are going to do, I'm going to show you how it is manual, how it is moving. All right, the weight is moving. So I will have a starting weight like we had in the example earlier. We had 0.61, 0.8, this kind of thing. But in my case, I will have a starting weight of 5. And I will update that weight of 5. That weight of 5 should be updated in such a way that it moves to the left to reach that optimal solution, which is here. All right, we want to reach that optimal solution, which is a weight of 0. This is our aim, to get a weight of 0. So how do I do that? I will write a series of codes here. Do not worry too much about what I'm writing here, but just observe it. C represent my starting weight. I'm calling it C 5. And I have my eta, which I explained to you. I'm going to just take an arbitrary value of 0.2 here for the time being. So insert, suppose I take eta to be 0.2, and then I will change this from time to time. All right. So these are the two things that you need to bear in mind, that C represent our starting weight, our first weight, initial weight, and eta represent the learning rate. And I'm just taking an arbitrary value of 0.2. Then the rest, you don't need to worry too much about it. As I said to you, you may wish to follow it. Let's suppose I'm going to run this model 50 times. All right, I'm going to run the iteration 50 times, which means that I will have a first initial weight, which is going to be 5. I will put a remark here. And then I will have the updated weight. The updated weight will move to the left. Then I will have another updated weight. I will do that 50 times as you are seeing here. This is what I'm trying to do here. Okay. To be able to do that, I will need to know what is my derivative. So the dy by dx, don't forget the d del ed by del w. This is what I want to do here, which is 2x, but I'm not going to get into the details of what I'm writing here, which is outside the scope of this module for the time being. So I'm just showing you something. You just need to focus on the end result, okay? Do not worry about what I'm writing down here. Um, x, yes, and then we have the system sleep. Put it as 1 second. Oh, no, it got 50. Let's put it as 0.1 second, and then we have the text that will be representing the c2 squared. And then, yeah, go. And then we have cx 0.2 or 0. No, let's leave it as, let's put it as, it should be 2 or 3. Comma. Here we go. You see, this is what is happening here. When I did that, okay, I'm just going to copy paste that. Just give me a second with you. I'm just going to copy paste that somewhere so that I can rerun it from time to time, right? So what I will do here, what I've just done here is, let me just change that system sleep to make it a little bit slower in the code that I have here. Let's put it as 1 second. Okay, I put it as 1 second. So just observe what's going to happen to the left. I'm going to repeat this line of code, and the initial weight is 5. I put a star here just to show you what's happening. And this is why we call it the gradient descent. It's going to descend toward the optimal solution. And then when you have updated the weight with a certain eta of 0.2, look at what happened. It goes here, and at some point in time, it starts to get to converge to the optimal solution. Start converging to the optimal solution. I've done that 50 times. So in other words, you have 50 dots here that you are seeing. I'm going to change this system sleep as I told you. I've already changed it in the copy here, and I'm putting it as 1 here. So we are going to run it. Now just observe what's going on. You see the first dot, the second dot, third dot, and it goes on. You will have it running 50 times. All right. At some point in time, you won't see clearly what's going to happen because it will converge toward the optimal solution. So this is what is happening. Each time, by using a value of eta is equal to 0.2, this is what is happening to the solution. It will move on and move on and move on until it converges to that particular point that you will see here. So it's taking some time because I've set the system sleep to be 1 second. I could have changed that, but I'm going to run it a little bit faster now with a different value of eta. So just bear in mind how things were for eta 0.2. And let me just show you what it is for eta equal to 1. Okay, I'm going to reduce the speed. I'm going to rerun the same thing now by copying. Rerun the same thing by changing the system sleep to 0.5 seconds. And then I'm going to show you, or let me put it as 0.5 seconds to reduce the time by half. And I will change the eta. I'll make it become, let's suppose 0.9. Or let's take it as 0.9. Yes, I'm going to take it as 0.9 and you see what's going to happen. Okay, I'm going to take it as 0.9. Just copy paste that. I'm going to run that code again with 0.9 as eta, and then I'll decrease the time so that it gets to run a little bit faster. So just please observe what's going to happen. You see now it starts overshooting the optimal solution and it moves to the left, and then it moves to the right and moves to the left. It keeps on oscillating all around. And this is what is happening here in this code. Now, I just want to show you a few other things in a moment. Apart from that, let me just show you something else as well, right? Uh, Maybe before I do that, let me try to show you what happens when it is eta equal to 1. All right, when it is eta equal to 1, let me just show you what happened. I'm going to reduce the time a little bit more again. I'm going to put the system time into less than 0.2 seconds. So let me just try this and show you. So you see, each time when you put eta equal to 1, you will see the values keep oscillating around and it never reaches the optimal solution. This is why you cannot put the you cannot use this function, this change in the weight without the eta. Without the eta, it will be keeping oscillating all around these two values. So this was a little bit what happened, but let me just show you something else as well, which is very important for you, which is also important rather. And I'm going to plot what we call a trace plot. I'm going to plot a trace plot. A trace plot for what purpose? To show you what is happening to these errors. What is happening to them in terms of values? All right. In terms of values, what is happening to the weights? All right. Are they converging to a particular value, or are they not converging? Like here, you see that there has been no convergence. They have kept on oscillating all around without reaching this optimal solution. So if you want to see what just happened here on a trace plot, I can just show you this. I do plot C and then I type equal to L. Type is equal to L. And then let me call it main is equal to trace plot. And then the X lab represent the number of iterations. Number of iterations means the number of times that it has run. Here we are running 50 times. So let's just have a look at what's going to happen here. You see, it keeps oscillating all around. Each time the value is at the same place. All right, it keeps moving around without never reaching an optimal solution. Now I'll do the same thing. I'll just copy paste that line of code, but I will do something else. I will add something to the code, which is a code power and throw. All right, don't worry about that. I'm just going to do the amendment in my code and run it again with uh, a value of 0.2. Let's suppose I take a value of 0.2 for the eta, and I'm going to take the value of 0.2 with the system sleep to be small now because I don't need it to be fast. I put it as 0.1, the system sleep, and I also put a value of 0.2 and I will play with it at times. I will change the value from 0.2 and at times make it becomes 0.9. Like here, you've seen the value for 1. So let me just play with this. I'm just going to write some piece of code, don't worry. And I will copy and paste what I've got here and do some amendment to it. Just a second with you. I will also plot the value of C as well, just for you to see what the values are. Give a value of C, so to get an idea of what it is. So I will put it as eta. I've just done some amendment to the coding and copy paste this. So let's have a look what's gonna happen here. I put it as eta is equal to 0.2 and a system sleep of 0.1, okay, as we've done originally. If I'm not mistaken, we did that originally, okay. So let me just run this code. So you see with 0.2, this is what's happening. And look at the trace plot now. You see here in the beginning, there is no convergence, but you will see that there is a consistent behavior where the where the weights are being updated to decrease to a certain point, and it converges. Here you see there is a convergence. The points stop at some point in time. There is no more change. At some point in time, there is no change, which means that you have reached an optimal solution. When you see something like this, when you see a behavior like that, you know that you've reached an optimal solution because at some point in time there is no change in the weights. So this is what happened when you see the trace plot here. Now I'll do the same thing but with a different value of eta, which is 0.9. Let's suppose 0.9. Let me just run the same code but now with 0.9. You see, there is again a lot of oscillation around, but at some point in time, nevertheless, there is a convergence. The convergence takes more time compared to what it was before. In the previous case, when it was 0.1, the oh Lord. When it was 0.1, there has been convergence as from the around the 10th or the 15th uh, iteration. But here convergence start as from around the 30th iteration onwards. So it takes more time before you get convergence, before you reach the optimal solution, in other words. It takes far more time than if you were to use the zero point 0.2. Now suppose I take another eta which is 0.02 or 0.01 rather, and let's see the way that it evolves. 0.01 might take some more time as well, I don't know. We'll see whether the 0.2 is the best solution than the 0.01. Let's have a look. You see, it's taking a lot of time to reach the optimal solution, and you will see that it has not reached the optimal solution. If you take 0.01 with only 50 iterations, it has not reached the optimal solution. So for an eta of 0.01, you need to increase the number of iterations to be able to reach that optimal solution. So it's not the best option because it's taking too much time to reach that optimal solution. So we've seen that in that particular example that we just took here, 0.2 sounds to be a good solution, right? We might try 0.1, but we can keep on playing with that. If you want, you can just make a pause of a video and copy and paste these codes and play with the value of eta and play with the value of eta. Yes, that's all you have to play with and see what happens, and you will see that it keeps on playing around. I can give you another example as well, but maybe some of the time, I don't know if I will have time to do that here, because I wanted to show you an example of a global minimum and a global max local minimum. So maybe I'll just take a pause on I'll make a pause on the video and write down a line some codes for you to show you that. Okay, so just give me, I'm just going to take a pause on the video. So I've written the code. Now, normally I've paused my video so that you do not see the time that I took to write the code. I'm just going to run a code. Um, now, I'm going to run the code with a polynomial, right, where you would have an example of what we call a global minima and a global maxima. So first of all, let me just run that for you to see what's going on, and I will plot the function just so that you can see what type of function I'm talking about. Let me just close that again and let me just rerun that file vertically. So here we go. Now you see another function here, which is a polynomial where you have a local minimum and a global minimum. So our aim is to reach that global minimum. I will show you a limitation of that method. So I will assume that my C is 1.5. I will assume that the C at the starting, the initialized weight is 1.5. And I will take a certain value of eta, let's suppose 0.01, and run that code. So I'm going to copy paste what I've written here. and do this whole thing again. Let me just close that so that you can rerun it. So here we go. Uh, so negative 1.5, all right, and the value of negative 1.5, not 1.5, sorry, but negative 1.5 started here, and it moved and it moved and it moved to the local minimum. So note well what has happened here. When you have initialized your value as negative 1.5, look at what has happened. It has reached the global minimum. You see, it has reached the global minimum, but it has not excuse me, not the global minimum, but the local minimum. It has reached the local minimum when you initialize your weight here. However, you did not reach the global minimum, and the aim is to reach the global minimum. We want to have that weight here, which minimizes the sum of squared errors, and this is the best weight, in fact, that minimizes the sum of squared errors, and we want to reach that. So, but unfortunately, with the method that we are taking here, there is a problem here. There is a problem because it depends on where you have initialized your weight. Where you have initialized your weight, what has happened is that your solution got stuck in what we call a local minimum. So if let's suppose now I put it as something like 2.2. By the way, look at the trace plot. There is convergence. There is a convergence. So you might think that you have reached the solution, the optimal solution, but it's not necessarily the optimal solution as well. This is one of the issues that we have with that method of when you just take this change in Wij that I just showed you. Let me just change a little bit. Let's suppose I put C as 2.1 or 2.5. C as 2.5. And let's run this whole line of code again. So you see that there is a big problem here. When I put 2.5, look at what has happened is that the weights has been updated in the beginning, but then it stopped updating. Why is it so? It's probably the case because the value of eta is too large. Maybe I need to rerun that line of code again with a smaller value of eta. Let me put it as 0.01 now and show you what's going to happen. Hopefully it works this time. Yes, you see, this time it works. By taking a value of 0.01, if you started by 2.5, it has moved to the optimal solution relatively fast, if you can say so, relatively fast, and there has been a convergence as from the early iterations itself. So that's a good value of eta that we've used here. So you see that in the case of a neural networks, you will see that later on, if you were to apply the neural network, this value of eta is very important. The learning rate is very important in such a way that you reach your optimal solution quickly or not too slowly. Now, the other problem that we have with that method is that you are not sure whether you've reached a global minimum. You might have got stuck in a local minimum as you've seen here. All right. This is one of the limitations of that method. This is why there is another term that you can add to this to this change in the weight. There is another term that you can add to the change in the weight, which is what we call the momentum. All right, that's another term that we can add, the momentum. But I'm not going to get into the concept of momentum here. So we have a gradient descent method as you've seen here. The next step is, so you have understood a little bit what this weight change in the weight is. I've done a small simulation to explain this to you. I hope you've understood this. And what we want to do now is to see how all this apply in a practical context. All right. That is, how do we make sense of all this in terms of our data? How do we make sense of all this when you have a data set in front of you and you have to apply all these different things? Are you going to do this differentiation? Are you going to do all these kinds of things? Differentiate your errors? Would you find your sum of squared errors, and do the derivative? How would you do all these? So, from a practical perspective, the gradient descent method can be applied through something that we call the backpropagation rule. So this is what we are going to discuss now. What is the backpropagation rule? We are going to discuss that now. The backpropagation is a rule that normally takes into account the error that you obtain at the output node, and it will percolate back this error through the network. That error that you obtain for the first pass in the neural network, it will take that error and will percolate it back through assigned responsibilities to different nodes, nodes which are connected to weights, obviously. And it will do that through the gradient descent method. Now, you might ask yourself, what am I talking about, and so on. We will get into that rule first and show you how it looks like, and then we will get into the details, especially the mathematical details, and also the application side of that rule. But quickly, the idea is the same as the backpropagation, as the gradient descent method that we just discussed, in that we want to have our updated weight, which is obtained through the current weight that we have, and we are going to add a change in the weight, and that change in the weight will be obtained through the gradient descent method, obviously. But the backpropagation rule will be applying the chain rule to um, obtain the derivative of the sum of squared errors with respect to the different weights, and we will get into that in a moment. But quickly, this is how we have two cases, by the way, for the backpropagation rule. These two cases are one case for the nodes, for the weights that are connected to the output nodes, and there is another case for the weights that are connected to the hidden nodes. All right. Uh, this is the second case for those that are hidden nodes. We will discuss the first one first of all. Let me just show you what I'm talking about before we get into this detail. The thing here is that you remember last time we discussed that in the first video, where you have different weights that are connected to the output node. These are the weights, the 0.9, the 0.9, and the 0.5. They are constant here, and they are the ones that are connected to the output nodes. And the way that we update these weights, they are going to be updated using this first rule that I just mentioned here. They will be updated using this first rule as you are seeing here. So what happened is that you will have your new weight, which will be the current weight, the 0.9, for example, over 0.5, plus a change in the weight, which is defined as this. How do we get that? What is all this about? We'll get into that in a moment. But this is what we want to do. We want to add with that term here, that value that we get from this formula. And then apart from that, obviously, there are other rules that applies. There are other rules as well. There are other weights that can be updated. For example, this weight, these different weights 0.61, 0.8, 0.58, and so on. These are weights that are updated using a second rule, which is the rule that is shown here. These are updated using that rule, that is not that rule, that case of a rule, which is training rule for hidden unit weights. Again, you would have your current weight plus the change in the weight, which is defined as you are seeing here. So the delta J, by the way, represent our error responsibility, all right? Error responsibility. This is what the delta J represent. And we also have our delta J, by the way, for this one. Our delta J for this one is this, and this represents the error responsibility that I was mentioning earlier. All right, just for information, you can keep that in the back of your mind because we might be coming to that again later on. So that part of this formula here, this part, not the eta and not the xij, that part is referred to as the error responsibility for the node j. All right, and here we have the error responsibility for the node j, which is given by this formula as you are seeing here. And we'll get into all this later on. So let's talk about the first thing. Let's talk about how do we get this. We'll discuss only for the output nodes. That is, for the weights related to the output node, this is what we were going to discuss the mathematical details behind only for that node. So that at least you get an idea where this whole rule comes from. You will, because we discussed the gradient descent method, and it will be a bit sad if we don't understand how this rule is related to the gradient descent method. So we'll get into that in the mathematical details. So what I ask you to do here is to derive that rule, right? To derive this rule mathematically, all right. Of course, to be able to derive this rule, you will be given certain information. First of all, what is all this rule about? You have your eta, which we already discussed. You have your tj, which represents your actual output, your actual targeted value, which is found in your data. And oj represents the one that you have predicted for tj, the one that you have predicted, which is found through the neural network. Example, you have 0.87 that you have predicted through the first pass in the neural network. This is your oj. And the tj represents your output. And we will get into an example later on, and I will show you we are going to consider tj to be 0.8. But this is just an example that I'm going to discuss afterward. But here, the idea is just to introduce to you these different terms. Eta represents your learning rate. Tj represents your output, your target output. And then oj represents your computed output, that is your predicted output. And xij represents, of course, the input from node I to node j. All right. If you are referring to a particular node output j, for us there is only one output node, so j would be equal to 1. But if there were two output nodes or more, you would have j taking different possibilities. For us, j is z. All right, we have only one output node, so we will have x, I, z. Each time we will have only one. If in the example that we took here, when we are going to apply, you will have only one z. But this is a general formula which applies for more than for one or more possibility. All right. This is why we put the j, because j could correspond to 1, 2, 3, or whatever number of possible output nodes that exist. But in our particular example, just remember that we have only one. And then I represent the different nodes that comes from the hidden nodes. For example, you have xaj. Xaj represent the input from node A to node J. Like from node A, xij means the I can be represented by node A here and J represented by Z, obviously. So A, Z, you have X1, Xaz represent the input from A to Z, and the input from A to Z is the output that you got here with 0.831. This is the input that you have, the Xaz value, right? You have the Xaz value. Then you have another input node, XBZ. XBZ represents the input from node B to node Z, and node B, the input from node B to node Z is the output that you obtain at B, which is 0.819. So you would finally get XBZ easily. And then you have X node Z. X node Z is the input that you have from the constant term rather to the node Z, and each time we are going to consider it as one, as we discussed in the beginning. For all these nodes that are not connected to, for all those weights that are not connected to any node, it's going to be considered as 1. We are using a value of 1. So x node z is going to be equal to 1. So here we go. We have understood the different terms in the formula. Xij represent our inputs from node A to node J, and J is the output node, obviously, because we are referring to output unit case here. All right. So J represents the output node, I represent what we had before, and then OJ, I just explained it to you. OJ represent your computed or your predicted value of Y, and TJ is your actual value of Y, and eta is the learning rate that I mentioned to you in the gradient descent method. You already see part of a gradient descent method appearing here through the eta, by the way. So let's get into the mathematical details behind. All right. You will see that I ask you to derive that rule. To be able to derive that rule, obviously, you will need to understand a few things. Remember that the change in the weight, according to what we've learned earlier, is defined as del ED by del WIJ. This is what we have studied. The change in the weight is represented not necessarily by del ED by del WIJ, but you also add negative eta as we did earlier in the gradient descent method. In the gradient descent method, this is what we studied. And what we want to do is we want to run this in such a way that we get this in the end. So the change in the weight is negative eta del ED by del WIJ, which is ED represent our error rate, which is defined as half of the sum of tk minus ok to the squared, where k represent the outputs. Bear in mind something is that for our particular example, there is only one output node, but this is a general formula that applies for one or two or three or whatever number of output nodes that you might have. So if you have to calculate errors, for example, uh, you would have to bear in mind that it's not always the case that you have only one error, but you might have more than one error. All right. So then you have OJ, which represent the output at node J. And the output at a certain node J, whatever node J you might be discussing, whether input, whether either or output. Of course, here we are referring to the output node, okay? So is defined by sigma net J. You remember 1 over 1 plus e power negative x. This is a sigmoid activation function. So sigma x was defined as this. Sigma x is equal to 1 upon 1 plus e power negative x. So OJ is the value that you get by replacing net J. You remember what I'm talking about here. This output that you got at Z is obtained by what? Is obtained by 1 upon 1 plus e power negative 1.9427. And how did we get that? So I got that as 1 over 1 plus e power negative 1.9427. And what we just did here is that to obtain this output, we have been taking the value of net z, which is obtained through the combination function, for the combination of these different inputs right here and into there. And we substituted this value into the function of sigma z, and we got our output. So here we are not putting it as z, but we are talking about oj is equal to sigma net j. Net j in our particular example is going to be net z. All right. So I repeat, it could be that you have more than one output nodes. So for our particular case, we have one, but it may be that you have more than one output node. So we are going to use these different information in view of obtaining what we have here. Of course, to be able to obtain what we have here is that we will need to go through that formula where everything begins. All right, we'll need to go through that formula where all begins. So let's start here. Okay. Here we are. We have a change in the weight, which is defined as negative eta del d by del wij. So this is what we have for the time being. Our next step is to work this out to be able to come up with the rule that I just showed you. Okay. So the thing that you need to understand is that if we could differentiate ED with respect to wij, if we could apply this partial derivative easily, things would have been so straightforward. But here you have to be careful. We can't differentiate ED with respect to wij. Why? Because the error term, there is no wij at all. Let me just rewrite the error term here for it to be clearer. So we have the ED, which is equal to 1 upon 2, the sum of K belonging to the output nodes, all right, into the targeted output Tk minus, okay, I'm just defining it as K here. We could have used another term if you wish, all right, to the square. This is what we define as the error term. So if you look at the error term, there is nowhere that you have a wij. This is why you need to apply the chain rule to be able to work this out. To be able to apply this derivative of del sub d by del wij, you will need to use the derivative. What is the derivative that you are going to use? The chain rule, sorry. You know that if you are going to apply the chain rule, that's the kind of thing that you are going to get. Here we are. What we need here in the denominator and what we need in the numerator. Now, ED is what? How, with what can you differentiate ED, and with what can you differentiate wij? Number one that you need to understand is that wij is normally influenced by, normally wij rather can influence the network only through netj. If you recall, just a minute, I was saying that wij influence the network only through netj. How you just recall, I guess you will remember that netj is equal to the sum of the i's of wij xij. All right. So this is what netj was about. The sum of the different values of I, wij, xij. For a particular j, whatever j could be, net z, for example, it would be all the sum of all the weights that are connected to node z. All right, with their corresponding inputs, and when you did the sum you would get the combination function that we had there. For example, let's have a look here, 1.942737. Now this is what we know. So in other words, if we know that if we basically know that wij rather influences can influence the network only through netj, then we can use the chain rule by stating this. At least we know that here we can differentiate netj with respect, we can obtain the partial derivative of netj with respect to xi, to wij, all right? You see here, wij. And then, of course, this will become del net j. Now, what happened here is we'll get into this one first, and then we'll talk about this part. This one is far easier to compute. So what is the partial derivative of net j with respect to wij, excuse me. So here, this is what? Del net j by del wij is equal to what? If you differentiate net j with respect to this, you will see that for a particular wij, the only thing that will happen, that will be left, is xij. For those who did not really understand what I just said, if you're talking about a differentiating net j with respect to a particular wij. Wij, you have different possibilities of wij. You have w1j, w2j, w3j, etc. If you're talking about ij, so you're talking about, let's suppose if you take this sum as it is, you get w1j plus x1j plus w2j x2j plus it goes on like that, w a k j x k j plus it goes on till w I j. I call it wij like that, okay, plus wij xij, where I could be any figure, any number. It could be 1, it could be 2. So if you are differentiating, let's suppose del net j with respect to del w1j, what would you have, okay, what would you have obtained? You would have obtained only this x1j, and then the rest will just cancel out automatically because they would become 0. So if you are differentiating with respect to wij, like here, wij, the rest cancels out, leaving you only xij that you have here. So this is how I got the xij if you did not get it clearly. Okay, let's move on. This was straightforward. The next step is to determine this del ed by del net j. How do we get the del ed by del net j? So here, if you look at the error term, you will see again there is no net j that connects this one. But net j can influence the network only through oj. How can it influence the network only through oj? Because oj is equal to 1 upon 1 plus e power negative net j, as we just saw in the previous notation that was given here. Here we go. So we see that oj is equal to sigma net j, which means that it is 1 upon 1 plus e power negative net j. So we know that we have this rule somewhere here. What do we do then? We are going to use the chain rule again for that particular one here. So what do we want to do? Is that I just said to you that OJ influencers can influence the network only through this OJ. Sorry, excuse me. That J can influence the network only through OJ, as you see here. So in other words, this becomes del OJ, del OJ. Here we are. This is done. The next step is to start doing the partial derivative of del ed by del oj, partial derivative of ed by oj, and the same thing we're going to do for oj by net j. Let's start by this one first. Okay, maybe I'll move on to the next slide here. Del ed by del oj. Now, how do we get del ed by del oj? How do we know what ed by oj represents? Excuse me, here we go. So if you want del ed by del oj, it's very simple. You have 1 upon 2, and then you have the sum of k belonging to the output, tk minus ok to the squared. So what you want to do here is you want to do to differentiate that term, of course, taking k to be representing j here. So you have half of sum of tj minus oj to the squared. You want to differentiate that, so 2 comes on this side, and the half disappears, leaving you with only the term that is of interest to you, which is that of j, because you are referring to k representing j. All right. To k representing j, so you would have here 2 comes here, so you have a sum of t j minus oj, because this will become 1. This will become 1 multiplied by the derivative of j is going to be equal to 1. So in other words, this whole thing here turns out to be equal to, as I just said to you here, it's going to be half multiplied by 2 into tj minus oj times the derivative of oj, which is negative 1 here. So let me just show you this again. So you have j in this equation. So having j in this equation gives you tj minus oj. So you have half of 2 of 2 times tj minus oj to the power of 1 times minus negative 1, the derivative of this, minus negative 1, which is here. And this is why you see that we are using this half, because later on the half will cancel out, making the equation neater. This is why we are taking this form of a function instead of using the sum of traditional one that you are used to. All right? So you are left with negative tj minus oj. There we go. So now when you've got that part done, we need to get into this part of determining del oj by del net j. So let's get into this one. So we want to, excuse me, we want to now differentiate that part here. Before we get into that part, let me just quickly rewrite this down here, just for information, to make things, it depends on you, but just for information, you may wish to look at this in a different way. It is 1 plus e power negative net j to the power of negative 1 as well. So now we want to differentiate that thing here. Here we go. Del oj by del net j. Negative 1 into 1 plus e power negative net j power negative 2. All right, bring this down there, negative 1 into 1 plus e power negative net j minus negative 2. Multiplied by, of course, the derivative of this, multiplied by the derivative of this. So it becomes, if you have negative x here, it becomes negative 1 e power negative x. So here we go. The negative sign disappears, obviously, as you see. And then the negative 2 here will go down. So we have e power negative net j over 1 plus e power negative net j to the squared. There we go. Now just bear in mind something else, is that you might wish also to understand something. If we just take the formula as it is here, we won't get that form, because that form of the formula contains oj, tj, and xij. So we've obtained xij already. We've obtained tj minus oj. So here we go, tj minus oj, we have xij. The only thing that you see now is that you have something like oj into 1 minus oj that needs to be included in the formula. And this is not the form of the formula that you have here. And this is why you have to be careful. You can't use this form as it is, but you need to make e power negative net j the subject of the formula here. By making e power negative net j the subject of formula, you will get 1 minus oj over oj, right? So just bring that here and uh, make e power negative net j the subject of formula. You get 1 minus oj over oj, okay? When we get that, what we want to do then is to replace all these by this new value. And this is what we get here. When we replace, just imagine you have 1 plus e power 1 over 1 plus e power negative net j to the squared. 1 over 1 plus e power negative net j to the squared is just oj to the squared, right? 1 over 1 plus e power negative net j to the squared is oj to the squared. Oj to the squared. Multiplied by, of course, the e power negative net j that we just obtained here, 1 of minus oj over oj. And this is equal to, of course, oj into 1 minus oj. Our last step is, given that we have all the different components of a chain rule, we can just bring all that together. Now, remember that we wanted to start here. We've got this component and this component, so we've obtained that component first. We've obtained that second component here through the chain rule again, and we want to bring all of this together to make the formula. So I'll repeat, you add del ed by del wij, which was obtained by del ed j times del net j over del wij. And you have all these different components that were obtained. So the del ed by del net j, as you have noted, del ed by del net j was obtained through these. Del ed by del net j was obtained through these two values here. Negative tj minus oj into oj into 1 minus oj. All right? So in other words, you have negative tj minus oj into oj minus 1 minus oj, excuse me. And then this was done by multiplying xij. So this is where you have del ed by del wij is obtained through that part of the formula. But of course, for us, what matters is eta is a change in delta wij, which is obtained by negative eta del ed by del wij, which in other words equal to the negative disappears, leaving you with tj minus oj into 1 minus oj. Here we go. Let me just write it down there and then I'll show you again. So you have negative eta times this formula. So you have eta, Here we go. This is our formula. The negative disappears with that negative. The eta comes in this formula here and leaving you with that rule as you have seen. So just remember that rule here. This is what we just saw. Tj minus oj into oj minus tj minus oj into oj into 1 minus oj multiplied by eta multiplied by xij. Tj minus oj into 1 minus oj multiplied by eta multiplied by xij. So what we just did here is that we have been applying the gradient descent method. The gradient descent method states this, that you need to take negative eta del ed by del wij. And through that del ED by del WIJ, we've come up with a rule that makes it easier for us to obtain updated weight. So our new weight Wij, let's call it like this, new is equal to Wij, correct? Plus this, what you got here, plus a change in Wij, which is negative eta del ED by del Wij, which is this rule here. I repeat, this is applied only for the output units for the time being. Then you have another rule for the uh, inner nodes that I'm going to get into afterward. But before I move on, it's always good that you understand something. I can write this down like that. Eta delta j, eta delta j, xij. I can write it down like that, where j, where delta j equal to tj minus oj into 1 minus oj. So it's important that you understand that part as well, because delta j is a component that you will need to compute. This is what we refer to as the error responsibility. Error responsibility, all right? So you will need to compute that error responsibility for each node if you have different output nodes. Like in the example we took earlier, you will see that there was only output node, so you will have only one error responsibility that you will need to compute for the output node. Okay, but of course, as I said to you, this is just for the output nodes. You have the same thing that goes for the hidden nodes. In our example here, you will have the error responsibility that is given here, through which you will need to compute it for for node A and for node B, because you add two hidden nodes. So this is how we get into the mathematical details behind how we got this. All right, it's very important that you understand this, because the gradient descent method is what you are doing here. You are applying the gradient descent method to come up with an algorithm that makes it easy for us to compute or to update these weights in the neural network. Okay, so we are going now to apply this rule number one, and then we are going to give a try to apply this rule. Okay, we are going to apply this rule secondly. We are going to get into that afterward, but let's start by applying this rule that we just got here. To be able to do so, we are going to take an example, and we are going to assume that our eta is 0.1, and we are going to assume that our tj, which is in fact tz for us, is equal to 0.8. Okay, we are assuming that the value of the output at node Z is 0.8, and we are assuming that the learning rate is equal to 0.1. So eta is 0.1, and the output node is obtained by TZ. So what do we want to do? We want to update these different weights from a practical perspective now, to see using the backpropagation rule. Okay, so let's try to do that now. To be able to do that, we'll start by determining delta Z. That is the error responsibility for node Z. The error responsibility for node Z, as we just saw earlier, as I said to you here, we are updating only the weights connected to the output node. Bear in mind, I just want to remind you this. These are the weight that we are updating, the 0.9, the 0.9, and the 0.5. All the others are not into this update for the time being. We are referring only to 0.9, 0.9, and 0.5 that are being updated using that case, that rule. So to be able to do so, we will need to use this formula, which says let's compute delta Z, which is obtained by Tj minus Oj into 1 minus Oj. So let's compute the tz minus oz into oz into 1 minus oz. If you had another output node, you would have had to compute it again for the other output node. So let's talk about the error responsibility for the output node, which is obtained by tz minus oz into oz times 1 minus oz. So tz is what? So let me just get back here. So delta z is equal to the tz minus oz. What is tz? Tz is the one that you expect, that is the value that you have in your data set, the true value that you have in the data set, which is 0.8 tz, minus what you have computed. Minus what you have computed means what? What did you compute as as what did you obtain as a computed z value? So this is what you obtain, the 0.87 4653. 0.874653 times O. Remember tz minus oz into oz times 1 minus oz. So oz is 0.874653 multiplied by 1 minus oz, 874653. This is what you need to do. All right, you will need to do that part here to obtain the first error responsibility that will be assigned to this node here. And when you've got that part done, the next step would be to multiply it by xi, multiplied by eta, multiplied by xij. That will give you the change in the weight. But of course, xij would be the input that you have for a particular weight at a particular point in time. So let's get into that in a moment, but let's compute the error responsibility first. So you are supposed to get negative 0.00818, all right? By the way, I've already computed all this. Let me just show you that in what I've just done here. So I've computed the delta z, which is here, which is obtained, which is negative 0.00818. Here we go. The next step is to update now. When you have obtained these different weight, remember that the change in the weights, all right, the change in the weights would be obtained by taking negative by taking eta times this times xij. Eta is 0.1 times this negative 0.0818, okay, negative eta, multiplied by xij. The xij will depend on what value you are updating and so on. So let me just show you that. Just remember that the error responsibility makes things far easier for us when you have already computed it. The next step is to obtain the eta, which is always going to be 0.1 in that particular case. But then you multiply by xij. The xij is where things can change. So, for example, let's talk about this 0.5, which is your current weight. You will have to update it with a new weight. This new weight that you would have to update would be obtained by taking 0.1 multiplied by negative 0.00818 multiplied by 1, because the input from node 0, the input from 0 to z is always equal to 1. So you will multiply by 1. That will give you the change in the weight. Now, when you got the change in the weight, what you will need to do, the new weight, that is a new W node Z, new, let's call it new like this, would be equal to the current W node Z, which is 0.5 that we've got here, plus that change here, which is in fact a negative value. So 0.1 times 0.00818 multiplied by 1. So the negative, I'll just put it down there. So this is what I got here, the 0.4491 something. So as I said, you take 0.5 plus 0.1, okay, times the delta z times bk, which is equal to 1. And this is what gives you this value of 0.49918 and so on. A new change in the weight. You would observe now that the value is negative. It's not negative, it's smaller than 0.5, which quite makes sense because your predicted value is above what is the actual value. So if your predicted value is above the actual value, obviously the weights would be updated in such a way that they will become smaller, so that in the second pass through the network, when you have updated all the weights, through the second pass in the neural network, you will get a smaller predicted output, obviously. All right. So that's the idea. You don't expect to have a higher value than 0.5 because your predicted output is above the actual value. So you expect to have a smaller value here. And we do the same thing for the 0.9. And how do we do the same thing for 0.9? To obtain the 0.9, we'll need to take, to obtain the updated weight for 0.9, we'll need to take 0.9. So W, we call it AZ here, WAZ, new is equal to 0.9 plus negative 0 plus, sorry, not negative, but plus 0.1 multiplied by negative 0.00818 multiplied by XAZ. And what is XAZ? XAZ is the input that we obtain from A to Z, which in other words is the output that you add at A, which is 0.78318 multiplied by 0.78318. All right. And this is what we get then, 0.9936. All right. So by applying this, 0.9 plus this, in other words, it becomes minus, you get the 0.8. Let me just show you the formula. You took 0.9 plus 0.1, which is eta, multiplied by delta z, which we computed already, multiplied by H8, which is the input from node A to node Z. All right, XAZ becomes that. And of course, I guess you would understand how I obtained this one by now. It will take 0.9 plus 0.1 times the delta z that you've already computed multiplied by the 0.81936. So this is how you have been able to update the weights that are connected to the output node. Of course, the next step is to do what now? The next step is to update the weights that are connected to the to the hidden nodes. The weights that are connected to the hidden nodes are the 0.5, 0.72, and so on and so on and so on. So this is what we want to do next. We want to update those different weights connected to the hidden node. So how are we going to do that now? To be able to do that, we won't be able to use that rule that we just used here. We won't be able to use that rule, I repeat. This rule is applied only for all the weights that are connected to the output node only. So to be able to to update the weights that are connected to the hidden node, what we do is that we have to use the second rule, the second case here of the rule, which is here. So the idea is the same. You will need to have your eta, your learning rate, multiplied by your delta J, which represents the error responsibility at a particular node. For our case, you will have two possible delta, one for node A, one for node B, multiplied by, of course, the input from node A to node B, not node A to node B, from the input from the first node in the input node times to node A, the inputs from the first node to node B, things like that. Okay. And the delta J is obtained by this formula, which is OJ into 1 minus OJ times the sum downstream of delta K wjk. Now, this is easy, this part here. This part is easy. If you want to find delta A, you will need to use OA into 1 minus OA. That is the output that you have at A into 1 minus the output that you have at A. And how do you get the output that you have at A? Of course, it is sigma net A that you have already computed. We'll get into that anyway afterward. Let's talk about that. This is where you have to be careful, because if you have two output nodes, so in our example, you had two hidden nodes that were connected to one output node, all right? But as I said to you, it may happen that you have more than one output node. Then what happened is that you would have this connection that goes for two different output nodes. And if you have these hidden nodes that are connected to two output nodes, this is why the sum becomes important, because the sum applies to the two different output nodes that you will have. You have A here, you have B here. Let's suppose you have Z1, you have Z2. In other words, when you are computing this delta A, all right, you will need to compute delta A by taking OA into 1 minus OA times the sum that you have, that is the sum that you have for delta K. WJK means what? Delta K, K downstream of node J, downstream of node J means what? What comes below node A? What comes below node A, of course, is node Z. If you have A, the node that is downstream of A is Z. So if you have downstream of A, you have two possible Z here. This is why you will have to do delta. Let me just write it down on the left here. Plus delta Z. It's not plus, but it is multiplied here. We have to multiply by delta Z. We have to multiply by delta Z, W A Z, because J is referring to A in that particular example here, W A Z, and then a plus, because it says that you need to add with delta Z1, excuse me here, it's delta Z1, plus you have to do the same thing, delta Z2, WAZ2, all right? This is what you would have had to do if you had more than two output nodes. But in our example, you would have observed that there is only one output node, so the sum is irrelevant in that particular context because you have only one output node. So if you have one output node, it becomes so straightforward. You will need to take Oj into 1 minus Oj times delta Z into WAZ, as simple as that. So let's start determining this delta A, delta B, and so on. Okay, let's try to get this delta A, delta B, etc. Let me just write it down here so that you can follow it clearly. So delta A is what we want to obtain here. We have delta A, which is what we want to obtain for node A, is obtained by taking the output at node A. What is the output at node A? The output at node A is the sigma net A that you have obtained. So the sigma net A is, in fact, the output at node A becomes the input for node Z. But the output at node A is 0.78318. 0.78318 multiplied by 1 minus 0.78318 multiplied by the sum downstream. As I said to you, if you had more than one node, you would have to add the two nodes' error responsibilities times the weight. But in this particular context, you have only one node downstream, so there is no sum. So, but what is K downstream? The K downstream is the node that you have downstream of A, which is Z, delta Z. And what is delta Z? Delta Z has already been computed earlier, which is negative 0.00818. multiplied by negative 0.00818. This is delta Z. So you are multiplying by delta Z times WAZ. Remember, you're looking for delta A. So delta A means you have J is represented by A, and K is represented by Z. So you have WAZ. What is WAZ? The weight that you have. But so you have WAZ, the weight that you have from A to Z. What is the weight that you have from A to Z? The weight that you have from A to Z is 0.9. The weight that you have from A to Z is 0.9. Please do not look at the updated weight. You need to look at the correct, the original one. Not look at the updated one. You need to look at the original one, which is 0.9. And this is what's supposed to give you negative 0.00125. Here we go. Negative 0.00125. So let me just show you the formula that I've done here. So you have the 0.78318 multiplied by 1 point minus 0.78318. So H8, which is 0.73 0.18 multiplied by 1 minus this, multiplied by 0.9, the weight downstream, multiplied by delta Z. Delta Z is negative 0.0818. This is what we got by this value, negative 0.0125. We are going to do the same thing for delta B, obviously. It's the same principle. The only difference is now delta B would not be 0.781 8318, but delta B, the value that you are going to use is going to be 0.81936, 81986. And then the other thing is that you would have a weight that is going to be 0.9 here, which is the same as the previous one. And the delta Z stays the same anyway. So let's have a look at the formula. So you will have to take the output at B, which is here, multiplied by 1 minus the output at B, multiplied by 0.9 again, because it's again 0.9, multiplied by K, 12, which is our delta Z. So we obtain the delta A, we obtain the delta B, which makes life far easier. This is what you need to do always when you have such type of questions where you have to do an update of a weight. Always find these error responsibilities first. Find the error responsibility for delta Z, find the error responsibility for delta B and delta A, or whatever you might have. And when you found these error responsibilities, then you can start updating the weights. I've already done it for these one. So what do you do for this one now? The principle is the same. You will see that you will need, when you have obtained delta A, you just need to multiply by eta x with the input. So what does it mean? What is eta for us? It's always 0.1. We already, if we want to update nodes that are, update weights that are connected to node A. Let's take this one, for example, the 0.5. We need to do what? We need to take the current weight, as you would have recalled, the current weight, plus, which is equal to the current weight, plus the change in the weight that is defined by this here. So for us, our current weight is 0.5 plus the change in the weight. We are referring to the 0.5 here. Plus the change in the weight is obtained by eta, which is 0.1. Multiplied by delta A, because we are referring to a node that is connected to A. So delta A is, as you observe here, negative 0.00125, multiplied by what? Multiplied by xij. Xij is what? We're talking about j representing A. So xij will depend on what node we are referring to here, x node A. For us, xij represent x node A because it's the constant term here. and it's always, as you would recall, equal to 1. So multiplied by 1. And this is what gives you the 0.49987, whatever. So what did you get the 0.899? So you take the current weight, which is 0.5, plus 0.1 times delta A times the input from the node 0 to A. If you want to update the 0.61, that is W1A, if you want to update W1A, that is 0.61, you want to update that. So to update that, this is what I wrote here in the formula. You take 0.61, the current weight, plus 0.1 times delta A times the input from node 1 to node A. The input from node 1 to node A is 0.39, and you get this value. And you can reapply this formula for B, where now you are going to use delta B, and so on. So you can check out these different values that you have here in this Excel sheet here. You will find it in on Google Classroom as backpropagation rule application. All right, you can find it on Google Classroom as a backpropagation rule application, and you can just do F2 on the Excel sheet at the particular bold value which represent our updated weights. You can just do F2, you will see the formula and try to understand it. If ever you have any difficulty, you can understand it there. So this is what we just did. We talked about the backpropagation rule, and then there is a termination criteria which you can read on your own, which is relatively straightforward, because updating those weights means that at certain point in time you will need to stop. Okay, and normally one of the things that I've explained to you is that you can look at the trace plot apart from the one that you are reading now. You can look at the trace plot to have an idea of whether you are doing something that is correct or not. But the termination criteria, you can work it out through the training data set and the testing set and compare the result that you get there. You can read that afterward on your own. So remember also that you can add a momentum term, but I'm not going to get into the details of what the momentum term is about, but I'm just mentioning it so that you remember that there is a limitation to this method, that it might get stuck in a local minimum, which is then a problem. And if you want to solve this limitation, you can add something that we call a momentum term to it to make it easier for you to reach a global minimum. But this is something that you can read on your own, but bear in mind that if you want to um, when you have when you have computed all these different weights, our next step then would be to recompute this final result by going through a second pass in the neural network. In other words, what you have to do now, your input will stay the same here, x1, etc. But what would happen is that this net A will change with respect to the new updated weight. The F net A will change as well with respect to the updated weight, because the net A would have changed. And then, of course, if the net A would have changed, the net Z would change, and the FZ would change. All of these will change. The net A, net sigma net Z, net B sigma net B, net Z sigma net Z will change with respect to the updated weight that you have. And then you will get an updated output. And this updated output would become an output closer to 0.8. Maybe not that much close, but it will become closer to 0.8. But then again, if it is closer to 0.8, it might be 0. I don't know, when you do it, you can try it yourself. You might get 0.87, which is a little bit closer to 0.8, but not that much. So what you want to do then is that you want to repeat that process again. This is what we call the first iteration. This is what we call the second iteration, the third iteration. You remember in the example of a gradient descent method I was talking about, you have a first iteration, second iteration, also referred to as epoch. All right. These iterations are also referred to as epoch. It's a technical term to refer to the different iterations. So you have a first pass through network, you have the first iteration that will occur, you will have a second iteration, the third iteration, and so on and so on. So at some point in time, you will need to stop. And how do you determine that stopping criteria? This is what I explained here that you can read on your own. So that's a little bit the end of the neural network. I hope you've been able to understand the principle. And if one day you need to apply it, you have different packages in R that enables you to apply this neural network. And these packages, of course, when you're applying them, you will need to take into account these different things like the learning rate that we learned in this course. And there are other things that you can do apart from the one that I explained here. There are things that we call sensitivity analysis that you can apply. Just try to make some sense of the results that you get from the neural network. Because the neural network, as you have seen here, it's just predicting an output, and that's mainly what you get. In the end, you will get a good predicted output, which is very close to the actual value. But on the other end, if you want to try and to understand a little bit about these different variables, which one has more impact on the result, if you want to see whether variable 1 has more impact on the final result or variable 2 has more impact and so on, there are other methods that we call that sensitivity analysis that you can apply. So that's all for neural network. Bye bye.